All right. Good morning, everyone. Thanks for joining for this IQUIS seminar. Today we have Dr. Pranav Gokhale. Pranav has a PhD in quantum computer science from the University of Chicago, where he worked with Fred Chong's group. He then co-founded and he was the CEO for Super.tech, which was acquired in 2022 by ColdQuanta, which is now Infleqtion. And Pranav is then the vice president for quantum software at Infleqtion. And today he's going to be telling us a little bit more about how they multiply the performance and utility of quantum hardware by using software co-designing. Thank you, Pranav.
Awesome. Thank you so much for having me. I appreciate the warm hospitality from Bruno, NCSA, Brian, many other names, Paul, Quiet, so forth. And it's my first time here on the UIUC campus, which is a shame because I read your research all the time, and it was a really pleasant train journey down. Is my microphone on? I probably should have checked this. So am I good? Okay. So testing 1, 2, 3. Well, it sounds like you can hear me. Okay, great. And then I think Zoom should be on too. So as Bruno mentioned, I'm going to talk today about force multiplying quantum hardware with software. And as I was walking around this morning meetings, people actually made a very last minute addition to my slides, which is I thought it'd be good if I introduce Infleqtion and who we are before I dive a little bit into the science. And as one piece of context, we're the largest company employing quantum talent in Illinois, as well as in the Midwest more broadly, and very eager to deepen our relations in Urbana-Champaign. So in terms of the hardware origin of the company, it's a cold atom, neutral atom based platform. The company used to be known as ColdQuanta. And one of the fun things about the neutral atom platform is that the same atoms that are used for qubits for computing can be used for atomic clocks, for inertial sensors, for RF receivers, and so forth. So it's a very versatile platform that's based on decade development of glass cell vacuum technology. Now I said on the software side, which is actually platform agnostic, and I won't talk too much about neutral atoms in this talk, but just helpful to give that context. We are a very global company. I'm based in Chicago and hoping to have relationships and hopefully even an office here at some point. Madison is our air correction test bed, and most of the people in our company are in Boulder, Colorado in the US, but we've also now, as of this year, have operations in the UK, Australia, in Japan, and in fact, oh, that's weird. Okay, it always works. We have on the International Space Station, we provided the cold atom unit for Bose-Einstein condensate, which is pretty cool. Some of our highlights in 2023, on the software side, I lead the development of Superstaq, which I'll talk more about, and that's our quantum software platform. Looks like I'll just paint through anytime. Okay, great. And then final slide about Infleqtion before I dive a little bit into the science part of this talk is we released our roadmap for quantum error correction a couple weeks ago. So in effect, we have a platform right now for which we expect to have 2 logical qubits with error detection by the end of this year. And in fact, we've already run experiments that sort of preliminarily validate that. But our intention is to scale up to hundreds of logical qubits, and that we anticipate happening in year 2028. We have investments in dual species test beds, as well as mid-circuit measurement approaches that should smooth this path. I'm going to dive now back into my original part of the talk, which is to tell you about where software fits into our picture of what quantum computing becomes, and perhaps also quantum sensing and atomic clocks become. Before that, I just want to remark that as I was coming down here on the train ride, I asked Reddit what I should see while I was here, and I was very impressed by all the cool things you have on campus. And I look forward to visiting the creek and the library and Silver Bullet later. So if anyone can point me to those afterwards, I'd really appreciate if you could point me to those. Always good to rely on the internet for recommendations. But all jokes aside, very impressed with campus and excited to talk to more of you. So I think I'm just going to skip the transitions and sort of unpaint the screen for my slides. But essentially, the core philosophy of what we're building on the software side and what our scientific worldview is that compilation for quantum computers and quantum programs is not a solved problem. And we say this because when we speak with people who are building quantum computers, the first instinct is that there's great open source tools, which is very much true, through libraries like Qiskit and Cirq and so forth. And they do a very good job of certain aspects of the quantum software stack, like decomposing quantum gates, routing and mapping and so forth. But what we also find is that most of these software tools do not go deep enough into the hardware part of the stack. And the key message from this talk, if you take away nothing else, is that we think that computer scientists and physicists need to be talking more, and that there are too many abstraction barriers right now between the quantum computer science and the quantum hardware. And so my goal today is to share with you a few vignettes of where software that is co-designed with quantum computing hardware can achieve up to 2 orders of magnitude of improvement in performance. And this is really important as we think about the path to quantum error correction. There's one path, which is to wait a decade for the device physics to get better, which it will. But there's another path, which is to combine the software with the device physics and get there faster. I have a second version of the title of my talk, which is the secret menu of quantum hardware. And what I hope to do is to really deep dive on one vignette of what do I mean by the secret menu of quantum hardware before kind of giving you a gallery view of just 7 or 8 different examples where we've encountered this philosophy going very far with quantum hardware. Secret menu of quantum hardware. So for those of you who like going to Taco Bell and Chipotle and so forth, you probably know that in addition to the advertised menu, there's often a secret menu which only the real connoisseurs and the real loyalists know about. And so for instance, at Taco Bell, you'll never see an enchilada on the menu, but it's there if you know who to ask. And there's a similar analogy actually in quantum computing and quantum hardware more generally. So if you go to, let's say, IBM or really any quantum computing vendor, including ourselves, you might see this as your standard menu. You've got a NOT gate with certain error rate. You've got an RZ parametric gate, a CNOT gate at market price, but that's it, and there's no substitutions. But if you're friends with the physicists on the ground, then you've got a secret hardware primitive menu. And so this might include things like on IBM hardware, instead of doing a CNOT gate, your fundamental 2-qubit gate may be a ZX Hamiltonian cross-resonance interaction that has a certain error rate. You might be able to do parametric 2-qubit gates where the amplitude of your drive is something that you can control in the software stack. You might even have a Q-trit transition or a Q-quart transition where instead of being limited to the qubit subspace, you can run algorithms that take advantage of higher modes. And in fact, I think one of the previous IQuest seminars addressed this topic. And there may be yet others if you have the right physicists to speak with. So what I'm going to do is talk through some examples of how when you have software that can address the so-called secret menu of quantum hardware, you can do a lot of performance optimizations that squeeze more mileage out of current quantum hardware. And I'm going to center my talk on 5 different hardware targets that we've worked with. That includes the Advanced Quantum Testbed at Berkeley, IBM Quantum, those are 2 superconducting platforms, as well as Rigetti, our own neutral atom quantum computer, which is now called Scorpius, and the trapped ion testbed at Sandia National Lab. I apologize for this unusual thing, but I think we'll get through it. So I'm going to start with a very deep dive on one result, which is now a preprint on arXiv. And this is about getting better swap gates on IBM hardware. And in short, many of you may know that swap gates, at least on current quantum hardware, dominate the actual execution of pretty much any quantum program, because with very limited connectivity, as you have on superconducting platforms, there's just a necessity of a lot of communication between qubits. And I'm going to see if I can drag my pen and maybe that will, no. Well, in any case, one preface is that I'm going to use a slightly strange notation in this piece of my talk. anytime there's a RZ gate, which is a Z rotation, rather than writing it out as a rectangle, I'm just going to put it in an arrow. And it doesn't really matter too much. Basically, the point that I want to make is that on many hardware platforms, including IBM's superconducting qubits, Z gates are done virtually, which means they have zero latency and zero error. And so I just want that visually to be much more narrow than a traditional gate. So for instance, this would be a RY negative 90 followed by an RZ negative 90 followed by an RY 180. And what I'm going to show you is that by compiling to the secret menu of quantum hardware, we can get swaps that are significantly faster and have lower error. And because swaps are so dominant, that actually compounds to very large improvements in overall quantum application performance. This actually won an award from IBM and is sort of recognized as their leading swap gate to be run on their hardware. And I'll even go further in saying that there's no catch in about what I'm about to show you. There's no custom pulses, no calibration required. So let me dive into, first off, the basics for performing a swap. And I'll do my transitions first so that the slide will clear in time. So in short, there's two ways that you could implement a swap. And this is what you'd see in any quantum computing textbook, Mike and Ike, let's say. Number one is to have three C-naughts in this direction. First, you have a C-naught, then you have a C-naught in the reverse direction, or a naught C, and then you have a third C-naught. But you could also do it in the reverse, or the inverted direction, where you have the controlled knot going up, then the controlled knot going down, and controlled knot going up. And typically, to standard software, off-the-shelf software, these two approaches are totally equivalent. There's no difference between them. However, when we look deeper into what the hardware stack is actually doing, there is a significant difference between them. Because it turns out that on many superconducting platforms, there isn't this notion of like a calibration of a gate this way and another calibration of a gate this way. On IBM hardware, they've calibrated unidirectionally with something called a cross-resonance gate. And a little bit further, basically, when you do a CNOT gate on IBM quantum hardware, what you're really doing is something called a cross-resonance interaction, which is a directed interaction. And it's prepended by some single qubit gates. And if you instead want the reverse direction of the CNOT, then you still have this cross-resonance pulse in the middle, but you now have a different set of sandwiching one qubit gates on the left and the right. And one thing you'd notice here is that if I look at the runtime of the CNOT versus the opposite, the NOT and then the C, then there's a difference. In the left-hand side, we only need one layer of single qubit gates. And in the right-hand side, we need two layers of single qubit gates. And because of that, the arithmetic is just that this approach on the left is actually a little bit faster than the slow approach. And you can even take this a step further. You can count the amount of so-called active one qubit rotation. Here you need 180 plus 90. On the other direction, you need 90 plus 90 plus 90 plus 90. So you get some savings when you do two of these instead of two of these. So this is a very simple example, but basically the takeaway here is that if you know which direction your cross-resonance gate is calibrated, then instead of calling swap Q0, Q1, it might be better to call swap Q1, Q0. And there's always a preferred orientation. And in fact, that preferred orientation does save you one entire layer of single qubit gates, as well as some active single qubit rotation. So it turns out that we can take this much further once we dive deep into understanding what this cross-resonance interaction is. And so in our paper, we kind of step through several examples that end up building towards a final optimized swap, which we call the CR polarity swap. And if I just highlight from top to bottom, the kind of optimization that we end up with a gate that is 3 single qubit layers faster, 2 instead of 5. And it has only 270 degrees of active one qubit rotation versus otherwise you'd need 990. Now, as you'll see later, this ends up giving a 10% reduction in the error of the swap gate. That's with interrelated randomized benchmarking, which doesn't sound like a lot perhaps, but two things that I'd emphasize here is that number one, 10% can be equivalent to a year of progress in terms of just device physics engineering. And the second thing is that swap gates build up so much. If you have a circuit that has just, let's say, 50 logical operations, but you haven't routed it yet, there's probably going to be 500 swap gates. So there's this sort of exponentially compounding effect of having 10% better per gate can make very large improvements in the overall runtime and error rate of an algorithm. Now, the slide transitions are going to make it a little bit tricky for me to show exactly some of these, so perhaps I'll only select one or two of the optimizations. I've already shown you how to go from a slow orientation to a fast orientation. Perhaps I'll kind of do this color-coded version. So a very simple thing that we can do is, now that we've selected the fast orientation, which has 2 of the C-naughts instead of the opposite orientation, we can kind of lay those out, and let's color code them so that blue is going to be the the C-naught pattern, and red is the not C. So C-naught, C-naught in between. When we have access to this level of granularity in the programming stack, and computer scientists might refer to this as a instruction set architecture in ISA, what you see is that there's opportunities for canceling out gates that didn't exist before. So a very simple instance is here. You've got a RX90 followed by an RX90. It turns out that on IBM's hardware, they've calibrated, this could be done as 2 Gaussian pulses that each rotate the qubit 90 degrees. But you could also just do a taller 180-degree pulse in the same width. And in fact, that's pre-calibrated. And that doesn't actually change anything about the total number of angles you rotate through, but it means that you only apply a gate once instead of twice. And then similarly, on this top set of qubits, there's actually a single qubit optimization you can do to cancel it out to just be a 1 qubit layer. And so what that looks like is these are the insertions that we're going to make. And you see that this is immediately going to shave off 1 layer of our single qubit gate apparatus and lead to fewer degrees that we have to rotate through. So this is the resulting gate. And I'll fast forward a little bit through some of the remaining optimizations. They get a little bit more gnarly. But one thing that you can do is you can apply commutativity identities, whereby these RXs commute through the bottom side of cross resonance. And that gets us to here, where we've got a swap implementation that's 2 single qubit layers faster and 200 some degrees of fewer rotation. And I think I'll skip over this next stage of optimization. You can probably, well, actually, okay, I'll show one because I think it really gets to the heart of this philosophy of going deeper into this physics stack. So far, I've been treating this cross-resonance object as a black box. And in reality, the way that IBM does 2-qubit gates is they do them in an echoed fashion. And this is actually something that's very common in the trapped ion world and other worlds as well, where if you want to do a gate, sometimes it's better to do half of the gate and then apply an X gate and do the other half of the gate in the opposite order. And it turns out that this ends up doing a version of the gate that is more robust to certain coherent errors. So one of the things we noticed is, well, if you think of this gate as a sandwich, you've got the bread is the half CR, the other bread is the other half CR, and the tomato is the RX180, then you can think about turning the sandwich over on its head, which would be to do the negative half pulse, then the X gate, then the positive half pulse. And it turns out that when you do that, you get extra opportunities for cancellation of gates. The reason for this is a little bit intricate, but it turns out that I'm lying a little bit here on the screen. This is not exactly a cross-resonance gate. It's a cross-resonance gate with a side effect in programmer speak. And so when you reverse this, you get a different side effect. And it turns out that different side effect can be good for gate cancellation. So essentially, instead of having 3 sandwiches that are all face up, you can reverse one of those sandwiches face down, and that cancels out this gate to the left. And what you're looking at here, it looks sort of bizarre, not just because of the sandwiches, but what we've got is provably the best possible swap gate you could ever do if you're the lowest you can go in the hardware stack is the cross-resonance interaction. And in fact, you can't go much lower because it turns out that it's fundamental that you need 3 fully entangling gates to perform a swap. So this looks very different from the original instantiation of a swap gate. You don't see the C0 happening here at all. But ultimately, this ends up being much closer to the fundamental limits of hardware. And what we're trying to evangelize is this idea that software should start addressing these layers of the stack, especially as we start to work towards quantum error correction, where every bit of margin that we have in error rate is going to be important to cut out whenever we can. So to show you a little bit about what this ultimately looks like to the hardware, what you're seeing here, so we built this software stack called Superstaq, and when we take a swap gate and compile it through Superstaq, we get the pulse schedule on the right-hand side, versus the standard 3 C0 sequence is on the left-hand side. What you see is the standard sequence takes about 4,400 DTs. Each DT is about 1/5 of a nanosecond, and our version is 4,000. So this is not a panacea. We're not getting it down to 0 nanoseconds, but again, we're able to achieve essentially the coherence-limited error rates. That is the main source of error on these qubits these days is just the runtime of the gate. And so if we can make the runtime faster, we make the error rate better as well. And you can see some of these optimizations that I just showed you in the gate level. You can see them quite clearly visually too. For instance, this chain of 2x gates or 2x90 gates gets compressed into a single gate. That the y-axis is a bit misleading, but these are the kinds of optimizations that we've been playing with. So we benchmarked this. I mentioned, I think in brief earlier, that we tried interleaved randomized benchmarking, which is sort of the gold standard for testing out swap gates. And what you're seeing here is every pair of 2 qubits that are connected on this particular chip with IBM. Standard is the gate error rate of a standard C0, C0, C0. And then optimized is our version that goes directly to the pulse level. And you can see across the board that we certainly don't get down to 0% error, but we're able to cut down a significant fraction of the error. And the dashed line that you're seeing here is we're wondering how much of this effect is because simply we made the gates faster, and how much of it is because we have fewer gates to run in the first place, independent of the runtime. That's called the coherence limit analysis. And without staring at this too much, we find that the majority of our improvement is because we make things faster. And just reiterating something, on superconducting qubits, the faster you make things, the better they run. So I'll skip a couple slides and just show you where this is being applied today. We have users from Argonne National Lab and Berkeley and Sandia who are running quantum programs on IBM through our software stack. And what they find is that as they go to larger and larger quantum programs, they see an improvement in the success probability of their programs when they run this optimized swap. But that said, it's not a cure-all. At some level, when you have too many swaps, and these were actually run a couple of years ago, so I think the data is better now. Eventually, you become so overwhelmed with noise that it doesn't matter anymore. But there is the sweet spot for 6, 7, 8 qubit algorithms where we get as much as 2, in fact, 10x improvements by having better swaps. Great. So that was my deep dive into one very specific example of how software engineering at this lower level of the device stack can lead to upstream wins. And I'm going to have a medium depth dive into another example also related to swaps before I dive into sort of a gallery of various examples. So I want to start by talking something called swap mirroring. And essentially, I want everyone to consider this very simple quantum circuit here, which is a sequence of 2 C0s in reverse order. Sometimes it's called a double C0. And one thing that I'm going to do, for no reason it seems, is to add a sequence of 2 swap gates after this. So this is legal. Doesn't really do anything because swaps cancel out. And it seems that I've made this quantum circuit significantly worse. But I'm going to take that last swap and implement it virtually. And what I mean by this is instead of actually performing quantum gates to do that swap, I'm just going to have a relabeling of the qubits so that Q1 is now on top, Q0 is on the bottom. And I've also expanded this swap into the 3 C0 decomposition that I showed earlier. So what you'll notice now is that there's some interesting cancellation opportunities. These 2 C0s are self-inverse, they cancel. And then these 2 C0s are self-inverse, they cancel. So the final piece of this circuit identity that's going to motivate something I'll show in the next slide is that this sequence of gates, which actually comes up quite a bit in quantum error correction, can be re-implemented as just a single C0 gate followed by a relabeling of qubits, a virtual swap. So that's kind of interesting and was, to our knowledge, never explicitly written down, but perhaps not that useful either. But it's interesting because oftentimes we don't really care at the end of a quantum circuit whether the qubits are in this order or this order. And sometimes in various programming languages, you can declare kind of don't cares of properties of your output. And if you have this don't care of insensitivity to the ordering of qubits, then there's many times where you can actually have the number of 2 qubit gates that you would need. So the slightly deeper thing I want to show next is that this approach, which we call swap mirroring, actually can go much further when we consider the device physics of hardware. And so I'm going to talk about a hardware platform that's actually one of our customers called QScout. It's a trapped ion testbed at Sandia National Laboratory. And whenever they want to run a arbitrary 2 qubit gate, they can take advantage of something called the KK decomposition. It's just a fancy way of saying that any 2 qubit operation can be written as a Hamiltonian, well, basically an XX interaction followed by a YY interaction followed by a ZZ interaction, where each of these is parametric. It has some exponent on it. It turns out that if you apply this swap mirroring approach to this very fundamental, this is the building block of every 2 qubit gate ever. Literally any 2 qubit gate can be written here. What if I multiply this by a swap? I intentionally do a virtual swap at the end. So it turns out when we do that, we have a relabeling of these single qubit gates, but more importantly, we have sort of a phase shift of the angles by which we need to apply these XX, YY, and ZZ interactions. So as a very simple example, let's say that the exponent of the ZZ interaction that we needed was pi over 4, that is, TZ is pi over 4. Well, in this version, that means that we wouldn't need any ZZ interaction at all because we have TZ minus pi 4. And there's some interesting analysis that you can do, and it turns out, perhaps not surprisingly, that if you take a complete sample, a hard random sample over every single 2 qubit unitary, exactly half the time, it's better to run it this way than to run it this way. So another way of saying this is any quantum program you could ever imagine, take the random space of quantum programs, half the time, it's actually better to intentionally add a swap gate, as long as you're OK with the side effect of having virtually relabeled qubits at the end. So that's kind of cool. We immediately thought of one very important, at least near-term quantum program that involves a lot of very random gates, and that's quantum volume. So quantum volume, for those who may or may not know, is essentially the prototype of a random quantum circuit, and you run it to declare that your quantum computer is better than other people's quantum computers, which has issues. But anyways, one of the things that we did with Sandia is we realized, well, we can take quantum volume circuits and tailor them for execution on the hardware primitives of their machine in a few different steps. The first step is that rather than the standard way that they were running 2 qubit gates, which was to apply 3 Mollmer-Sorensen interactions, pi half radians, they can instead take this parametric approach, whereby this is where we apply Mollmer-Sorensen by theta rather than pi half. This is kind of just the previous slide that I showed. But then the really interesting thing is this mirror swap technique, where now half of those Mollmer-Sorensen gates are going to be faster, better, cheaper with swap mirroring. And here's the best part: in quantum in quantum volume circuits, there's a totally random permutation of qubits between rounds. And so we're always insensitive to what the labeling of qubits is in the next round. We've also done some work with gate ranking with them, but let me show you some of the experimental results that will be published in hopefully the next few weeks. So what you're seeing here is essentially the plot that determines whether or not a certain quantum volume has been achieved. So there's this red dashed line, which is the bar that we need to cross to be able to declare a quantum volume, in this case of 16. And we need, as we go to the right, that's running more and more experiments, we need to cross that red line with what our average so-called heavy output probability is. But we also need to cross that line with statistical confidence. That is, the upper and lower envelope. The lower envelope also crosses the pink line. And you see that when they run 200 circuits with the standard compiler approach, they do not cross the lower envelope. At some point, it probably would, but that might be tens of thousands of circuits. With our first pass of compilation, what they're able to get, and this is in purple, is a crossover point at exactly 199 circuits. And this was very lucky, actually, because we ran exactly 200 circuits. But they were able to declare that they have quantum volume of 16. This is using this compilation to the parametric Mollmer-Sorensen gate. And then finally, that's just a view of just the purples. And then finally, with this mirror circuit, where they intentionally add swap gates, they're able to get the crossover point happening at 131. So the way I think about this is, without compilation that's aware of the underlying device physics, they're not able to declare quantum volume 16. With compilation that's looking at, let's say, 50% of device physics, they can get just at the boundary of declaring quantum volume 16. And with 80% of the device physics considered, at least the relevant ones, they can easily declare quantum volume of 16. And that's all three plots together. So the next example I'm going to switch to is work that we've done with the Advanced Quantum Testbed at Berkeley. This is a superconducting lab. And I had some nice conversations earlier this morning with the superconducting group and frame tracking a little bit. So this will be relevant to that. So I've talked a little bit about this aspect that Z-gates are done virtually on many quantum computing platforms. But there's actually a lot of subtlety to that that often gets swept under the rug. And so what you're seeing on the screen here is the standard way of running any one qubit gate ever, which is you apply 2x physical pulses, both are pi half radians. And before and after that, you've got these Z gates. And it turns out that with the right phases on these Z gates, you can implement any single qubit unitary. So that approach is pretty dominant right now, but I'll show you that it's going to have some issues. So first off, let's say that the single qubit gate is followed by a controlled Z gate, which is this one right here. It actually turns out that this is going to be okay. And the reason is that these virtual Z gates can commute through these controlled Z gates. Z commutes with Z. And you can basically push it all the way to the end of a circuit. And in fact, you can keep doing that until you hit a measurement block. And it turns out that measurements absorb Zs. And our Z rotation has no impact on measurement statistics. So that's kind of the prevailing way that people are currently using virtual gates in quantum computing hardware. But there's a big issue, which is, what if you have a 2-qubit gate that has some interesting device physics and is not a controlled Z? So let's say it does not commute with that RZ gate. Then we're in trouble because we're sort of stuck. There's nothing seemingly that we can do. And in fact, this is a real problem that many superconducting qubit firms are running into. If you look at gates like an I-swap interaction or a B gate, Berkeley gate, which is one of the most interesting gates out there, they don't commute with the Z, and you can't use virtual gates. There's an alternative, which is there's a different way of decomposing any sort of single qubit gate called a PMW decomposition that stands for phased microwave. And what it requires you to do is to have now 1, 2, 3, 4, 3 depending on how you look at it, physical gates. So that seems bad. But the good news is that at the end of this decomposition, you've got this virtual RZ gate, which sort of zeroes out all of your previous virtual phase. And so what that means is, and I'll skip over some of the slides that show this in detail, but in short, we can put this into any arbitrary 2-qubit compilation stack, even if it doesn't commute, because when this gets run, we don't have to worry about a trailing virtual phase that needs to commute with an arbitrary 2-qubit gate. There is no trailing phase that we have to commute through. So this is a little bit of a preview as well to work that we've got ongoing, and you'll see some of the first rigorous benchmarks of I-swap gates, Berkeley gates, B gates, and so forth coming as a result of this work. And again, this is somewhere where I think the computer science abstraction can go much deeper. And by building in assumptions about and awareness about the virtual gates, the software stack above can do a much better job with compilation. All right, the penultimate example that I have today is also on the Advanced Quantum Testbed platform. This is called the bring your own gate set approach. And in short, I'll show the result right here. One thing that we did recently is we implemented, to our knowledge, the first ever swap between qubits. I think I know one of the previous IQuest talks was about qubits, so this may be familiar, but essentially the idea is instead of being stuck to the qubit subspace, what if we could have exquisite control over 0, 1, and 2? And in fact, in some of my previous work, we showed that that can actually lead to asymptotic advantages, somewhat surprisingly, for higher level algorithms. But in that work, one of the biggest roadblocks was always no one had ever done gates between 2 qubits, at least in a reasonably high fidelity manner. What you're seeing here is what we call the truth table fidelity for the first ever qubit swap. So for instance, if I focus on this 83% block here, this is saying that if we pass in the 2-1 state, which is the third level on one qubit, the second level on the other qubit, and we read out, we get the 1-2 state as output. It's not perfect. Overall, the truth table fidelity is about 74%, but it is kind of cool because it builds building blocks towards bigger algorithms based on qubits. Now, when we first ran this, it did not look anything like this. And the reason is we required a very complicated pulse sequence. What you're seeing here are something called Kerr interactions or cross-Kerr interactions. And every pair of humps here represents essentially the controlled Z analog on qubits. And if you look at it, you see that there's 1, 2, 3, 4, 5 controlled Z type gates here. So this is technically correct in the sense that if you multiply the unitaries of these gates, you do get a swap. And this is very similar to the analog of a swap needs 3 C0s or 3 CZs in qubit land. In qubit land, a swap turns out needs 5 CZs or C0s, and that's what's happening here. But what we realized is that what we're really doing is we're forcing them to take this perfectly good gate here, which has a known unitary, and we're forcing them to put it in this controlled Z abstraction just because it's the standard computer science way of implementing a qubit swap. And a much better way is to actually use numerical synthesis and optimal control to find what is the best way to take this raw unitary here, conjugate it with single qubit gates, and then get a qubit swap. And so this is the core figure from our paper. What you're seeing here is our version of a qubit swap, which no longer has these pairs of echoed pulses. But that's fine because we just need a qubit interaction. And it turns out if you string together 6 of those, 6 half pulses, then you're able to get a qubit swap that happens 2 times faster and with fewer single qubit gates in between. And this is how we ultimately got our qubit swap. So this is published in a paper that we put out last year. And if people are interested in qubit experiments, I think AQT is, at least in my experience, the leader in this field right now. Great. So the last thing I'm going to show is actually our own hardware platform, which is our Hilbert or Scorpius neutral atom hardware platform. And I'll just mention a little bit about what makes compilation challenging on this platform, but also interesting to work on. Okay. It looks like the slide is missing, so I'm instead just going to mention very quickly that one of the challenges and opportunities on neutral atoms is that single qubit gates are generally done in a global fashion. That means that when I apply a gate to a certain qubit, let's say an RX gate, it's actually going to be, the only way I can do it is to apply it to every single qubit. In some cases, this is a good thing, because imagine preparing a uniform superposition that is a Hadamard in every single qubit. It's great if we do all of them in parallel. That's a very natural thing. In many other cases, though, we often don't want to have a certain qubit addressed by a global pulse. And so one of the ongoing compilation challenges is, how can we build a programming language framework that sort of is forced to address every single qubit at once? There's some nice theory that we can show that you can sort of exclude single qubits out of a global pulse by applying 2 of them and then having a cancellation between those 2 pulses. But this is more of an ongoing research area where we're actually trying to leverage some GPU tools where you also have some single instruction, multiple data that's enforced, and we don't sometimes want that to occur. So this is just another instance of where the device physics is actually percolating up the stack to the software. And I think we can make a big difference if we throw the right compilers at this problem. The last thing that I want to show is just an example, if it loads, of how our platform today operates. And let's see if it runs. So what you're seeing here is an instance of one of our users running through our compiler on the IBM Brisbane quantum computer. This is a 27-qubit machine, I think. And if you can excuse the fuzziness, they're running a 15-qubit GHZ circuit. When they compile with our stack, we actually produce a pulse sequence that goes down to the cross-resonance gates that I mentioned earlier. And when you see this drawn out, it's actually going to look very complicated. You see the pulses are going to have all sorts of interactions, including dynamically decoupling sequences. Those are those green humps in between. And the rest of the screen share is just running that same program through the IBM Qiskit runtime stack, which does a lot of good things, but it just doesn't get as low into the hardware. And so when one of our users ran this, this is from Argonne, they found a very substantial improvement in fidelity using this low-level compiler versus otherwise. And so you're going to see those outcomes in the next moment. This is sped up, of course. Actually sat in queue for a couple hours. But if you can see that, there's a fidelity of 43% with Superstaq versus 2.7% with Qiskit runtime. And for instance, the ideal outcome distribution is 50-50, all zeros, all ones. With our compiler, we're able to get 23% and 20% versus total noise with just Qiskit runtime. So the point that I want people to take home away with is that ultimately these techniques and optimizations that compile down from applications down to the very low level of control can lead to very important performance enhancements for near-term algorithms, as well as for quantum error correction, getting us closer to the threshold. This is the result that came out of that screen share that I was just showing, where the Argonne team was actually able to set a new record in how much fidelity they could get for simulating the water molecule with a VQE type experiment. So something that we're very excited about. And again, my message to the folks here is computer scientists and physicists need to talk to each other more. I think that any software that we can build that makes the lowest levels of stack visible to the software can be very impactful for downstream performance. So with that, I want to thank everyone for coming out today. I have my email address here, and I really want to sincerely mention that we're eager to engage with IQuest and UIUC and NCSA. So happy to take any questions and take any emails or any conversations downstream as well. Many of the examples that I mentioned today are either in this paper, which the archive link should load for, or they're referenced to from that paper, and I'm happy to take any questions. Thank you.
Questions from the audience? Okay, I do have a question now. So, and there, it's grounded on classical computing, right? But when you're doing these compilations, optimizations, there's some trade-offs that you have to do classically, right? You can think about threading loops and things like that, but then you might be taking a hit on memory caches and caches, hits and misses. What are some of the trade-offs that you see here on the quantum scenario?
Yeah, very good question. So in short, our current philosophy is that we're willing to take any trade-off on the classical side because almost every program that we run is going to be limited by the quantum fidelity, as opposed to we're willing to invest hours of classical compilation if we get even 3% improvements in fewer gate counts, things like that. That said, we're going to be entering an era, especially with quantum error correction, where that's not going to fly anymore. And so we're starting to prepare for the scenario where, especially for quantum error correction, we may need partitioning. So instead of trying to compile the entire 1,000-qubit circuit, just focus on blocks of surface code patches, compile the heck out of that, and then step back from there. I think this is also going to be sensitive to the latency requirements for individual platforms. On our own hardware platform, our gates take about a microsecond to 100 microseconds for the slowest gates, which isn't horrible. There's good and bad things there. The good thing is that our compiler and co-processing stack on the classical stack doesn't need to be like an ASIC today. The bad news is it means that our entire logical gate speed is going to be quite limited compared to what you could get with superconducting qubits. So we haven't personally invested a lot into like the caching layer and the some of the nanosecond latency classical parts of the stack.
So
I see Paul.
Oh, sorry, Paul. Go ahead. So Paul's question is about the hardware being optimized after the compilation is done, and how do you deal with that?
Right. In fact, this is absolutely something that has happened. Most of the approaches that I showed today, I didn't show the full backing layer, but usually we have optimizers, things like SMT solvers and frameworks that are equipped with any sort of changes in the underlying parameters. It does mean that we have to rerun that framework anytime there's changes to this kind of behavior. But actually, that's something that, because a lot of our heritage is in the superconducting world, where literally fidelities will change minute to minute or hour to hour, we've had to deal with in the past. I think the fundamental changes would be more challenging. Let's say, for instance, there's a breakthrough in I'm making this up, like mid-circuit measurement fidelities. That would actually change a lot of how we think about what the trade-off is between when and when we should not use mid-circuit measurements. There's a lot of cases where the depth of our quantum circuits can be reduced even asymptotically with mid-circuit measurements, but it's a bad trade-off right now. We would have to rethink it if some of those fundamental assumptions changed. Yeah, good.
Which is about one of the swap optimizations that Pranav showed.
Yeah, good. So I should have added a clarifying comment, which is that you're right. 50% of the time, it's better to do swap mirroring. The other 50%, we know in advance when that's coming up. So we compile it and we just don't do swap mirroring. So it would make it worse or it would be entirely equivalent if we did for 50%, for all of them, we did swap mirroring. We'd get no advantage. We wouldn't get a reduction performance either. But what we actually do is the 50% that we see in advance that we're going to improve from swap mirroring, we apply it there.
Another one, it's so on classical compilers, again, you leave some of the optimization levels to the user, right? You can say optimize 1, 2, 3, whatever. How is Superstaq dealing with that? Can you tune the amount of optimization that you can do?
Yes, so we have flags for turning off optimization. And also one thing that's especially important is barriers. So in fact, a good example of this is randomized benchmarking, which I referenced earlier. This is intentionally running repeated patterns of gates over and over again to cause a decay curve. And there's actually some compilers out there that they look at a circuit that has these barriers that are intended to prevent optimization. They're like, oh, let's just remove those. And it's a really bad idea because then it seems like you have infinite or 100% fidelity gates. So yeah, we have flags that turn off optimization and always respect barriers because that's actually really important for making sure that you measure decay curves correctly.
We have a question from the online audience. Santiago, please go ahead.
Hi, Pranav. Thank you for being with us today. The question that I have is, this kind of work evidently needs a lot of pulse level programming training. In your experience, what are the gaps? What are gaps presently in what people know, and what should we do as universities to move in a better direction so that we prepare people for the right kind of optimization at this level?
Yeah, Santiago, great question. I think part of it is first, we as a developer community need to build better pulse simulators. But the other thing is that I think not everyone needs to know pulse programming. We have to have good tools that enable generation of pulses, but users don't necessarily need to interact with those pulses directly. Now, that said, that sort of flies in the face of everything else I was showing here. So I think one thing I'll tip my hat to, I didn't work on it, but there's a really nice library on GitHub that's open source that's like Pulse Studio or something like that. And it's basically a way to visually go in and sort of draw pulses, see how they could run on a waveform generator and stuff. That may be a nice educational platform. I think that IBM's tutorials are decent for Pulse, but maybe it's something that people in this room can get together and write some nice open source tutorials or notebooks that show how to go a step further. I think maybe there's even a world where some intro physics classes or second physics classes and computer science classes show some of that pulse abstraction at a level that hasn't previously been covered before.
One more question from Marius.
I try to ask whether you can do small rotations with this procedure well, right? So small Z rotations. I'm really looking at very small values, and my introductory computers class doesn't cover that yet, right? So I mean,
yeah, in short, small Z angles are quite compatible with virtual phases. And so on IBM hardware, for instance, I would guess their resolution of Z gates is pretty much the same as their resolution on their waveform generator, which is probably at least 10 to the negative 5, 10 to the negative 6. Small X angles tends to become a little bit more challenging because it means you're sensitive to some pulse amplitude modulation. And I would say small Z angles, though, is pretty much equivalent anyways with some single qubit rotations. Ultimately, though, you're going to be susceptible to shot rate limits. If you want to distinguish a 10 to the negative 6 Z angle change, you're probably going to need 10 to the 9 shots to really suss that out. But in principle, Z angles are probably the way to do it.
thanks.
Mm-hmm.
All right, let's thank Pranav.